Howdy, everybody. Marci is usually doing these introductions, but Marci is traveling, so she asked me to introduce Bo, and she almost needs no introduction. Bo Li is professor and chair in the Department of Statistics at the University of Illinois, Urbana-Champaign. She is also Richard and Margaret Romano professorial scholar. She received her PhD in statistics from Texas A&M University in 2006 under the advisement of Michael Sherman and Ray Carroll, and then became a postdoc at National Center for Atmospheric Research, NCAR, before joining Purdue, becoming a Boilermaker as an assistant professor in 2008. In 2013, she moved to the University of Illinois, Urbana-Champaign. Dr. Li's research mainly focuses on spatial and spatiotemporal statistics and environmental statistics concerning problems in climatology, atmospheric sciences, public health, forestry, and agriculture. Dr. Li was the recipient of Young Investigator Award and Distinguished Achievement Award from ASA section on statistics and the environment. And she's a fellow of the American Statistical Association. She was also our 2020 H.O. Hartley Award winner from Texas A&M University. I am presenting to you Bo Li. She's going to talk about statistics, methods for climate change, and sustainability. Bo.
All right. Thank you so much. It's my great honor to speak here for the Farmers Student Network. And thank Brandy for the nice introduction, and thank Marcy Johnson for inviting me, who couldn't make it today, unfortunately. And also I want to thank Elen for organizing this and setting everything up. So since this is for the former students network, so I would like to take a few minutes to reminisce about my time at Texas A&M. I joined in spring of 2002. So this one was me when I was a student. I received a master's degree in May of 2004 under supervision of Professor Darren Klein. I still remember the time I went to his office asking him whether he can be my master advisor. He asked me, "Why do you pick me?" I said, "Because I think you look nice." I don't think this is the greatest answer, but that was the most honest answer, because I remember by that time, I took maybe 2 or 3 courses from Darren, and I really respect and like him. For my PhD, I mainly worked on spatial statistics with Professor Michael Sherman, and Ray is also my advisor. So this is not the greatest picture for Michael. But I searched online, and unfortunately, this is the only picture available online for him. But this is different from the Michael I knew like when I was a student. And then I have to admit that I haven't written a paper with Ray, but he has provided me so much help and a mentorship, and saved me a couple of times. I remember the first time I talked to him, he asked me, what did you do before coming to Texas A&M? I said, I was an engineer building ships in a shipyard company. So I was an engineer. I was trained as an engineer in China and worked in a shipyard company for a few years. And then he asked me, does the boat you built still float? So that was another question I was prepared for, but that helped me to relax a little bit when I was talking to him. So he's always very down to earth and fun to talk with. Finally, as every other student, I think we all have a common mentor, Professor Michael Longnecker. In addition to taking 2 semester courses from him, the experiment design course, very famous one. So Professor Longnecker has earned his retirement. So I feel fortunate that I still had a chance to take classes from him before it was too late. Okay, I wanted to briefly give an overview of my research before I get onto the examples. I worked on spatial statistics when I was a student, and 16 years later, I still like this topic and I still work on it. And I also developed interdisciplinary research with many other fields. So for spatial statistics, I still work on the theory and methods for univariate and multivariate spatial data and how to mainly focus on the dependence structure or the covariance structure of such data. And also, recently I started to bring functional data analysis techniques to spatial data, and also to study some issues of functional data indexed by spatial locations. I'm also interested in doing the multiple testing for spatial data, mainly motivated by climate model validation, how to compare different climate fields. Now extremes has received so much attention due to the natural disasters. So I work on spatial extremes, mainly on return value estimation. And Bayesian modeling. So I recently used a lot of Bayesian modeling in my research. I was not trained as a Bayesian statistician. I don't remember I formally take any Bayesian course, but I did sit in Professor Jeff Hart's course to get a basic understanding of Bayesian. And that has helped me so much even for today. And for the interdisciplinary research areas, also started when I was a student. I worked on Texas rainfall data, and I was also research assistant for Department of Public Health for 1 year, working on working on the pesticide control and children cancer. So, and then after I became a postdoc at National Center for Atmospheric Research, I continued to work on climate problem and worked on heat wave related morbidity. And recently I work on some other like HIV disease and also vector-borne disease like West Nile virus. And I also work on the agriculture data and the forest data. So basically, I'm interested in anything related to environmental sciences. I also want to take this chance to thank some of my former students and my current students and my wonderful collaborators who has worked with me in the past few years. I'm particularly wanted to say that I'm very proud. One of my former students, Trevor Harris, now is assistant professor in the Department of Statistics at Texas A&M University. Thank Brandy for taking him. I'm glad that he became the second generation Aggie now. Okay, so I will start it with the first project. I plan to talk about three projects if I have time. So the first one is about paleoecology. So we will basically is how to use data fusion to answer the question about the refugee in the glacial period. So I believe everyone has heard a lot about climate change and what could be the most possible drivers for climate change. Scientists have been very worried that the anthropogenic climate change will kill many species and eventually will damage the sustainability of our current ecosystem. So how to in order to best understand how climate change change the current biodiversity and also how to project the future ecosystem, we should look at the past using the paleo records to understand how the what would be the biotic responses to climate variation in the past. And if we can understand that, and then we would have a much better idea about the future. And the time period that we're looking at in my talk is the last glacial maxima period. So in order to show what this period, when this period is in the past, I made this very simple diagram. So you can see that from 2.58 million years ago, we're in the Quaternary, and the Quaternary has two phases. The first is Pleistocene, and ended at 11.7 thousand years ago, and we're now in the Holocene period. And in the later time of Pleistocene, that was LGM, the last glacial maximum. So this is the last period that the Earth is covered by ice sheet to the greatest extent. So we're going to look at how the species has been changed by the varying climates during this period. So roughly it's from 33,000 years ago to 33,000 to 20,000 years ago. And the problem that I'm working on is kind of like motivated by Quaternary conundrum. So it was previously believed that during the glacial period in the LGM, no species can survive in the high latitude area in the northern part or in the southern part of the Earth. And all the species currently in those areas are the species that have been survived in the south part and then kind of like moved to the north after the ice sheet receded. However, there is very little evidence to show the species extinction during the glacial period. So this kind of create a puzzle. So what happened? And then now more and more evidence actually pointed to the presence of cryptic refugee that could hidden somewhere in the high latitude areas. And then when ice sheet retreated, the species survived in the cryptic refugee, expand and prosper. So that's how it contributed to the current biodiversity. And the East Beringia, this is an area that has appeared in many literature, and so it has a high chance that this region is one of the areas that has cryptic refugee. And the East Beringia includes the area of Alaska and adjacent area in Canada. So although there is evidence that this region has cryptic refugee, but we don't know where the refugee would be. So my talk will focus on studying where the cryptic refugee would be in the Eastern Beringia area. So I will focus on two species. One is a green alder and the other one is a white spruce. So for each of those two data, we have three data sources to study the refugee. One is the pollen records, pollen fossil records, and the other is the genetic data and the species distribution models. So the first two are observations, and the last one is just computer models based on the relationship of climate and the species, based on like they calculate the probability of species, whether species could survive based on what are the suitable climate for such species. And so this column shows the data for green alder, and this shows for white spruce. So for the first, let's look at this one. For the first one, this shows the genetic and the pollen data. The genetic are the green circles, and the pollen are the triangles. And the lower panel shows the SDM, the species distribution model. So you can see that the pollen and genetic data are very sparse, the same for two species. But the SDM data, they are very dense, basically give you a map. However, this map is dense, but it's not very reliable. And the observation data, the pollen and the genetic, those are much more reliable than the SDM data. And arguably, genetic probably is more reliable than the pollen data. So each line of those three evidences have their strengths and weaknesses. So some are dense, some are sparse, but some are more reliable, some are less trustworthy. So we hope to develop integrative methods that can combine the strength of all those three data sources to come up with a map of a probability to show that whether each individual location could be a cryptic refugee in the past. So we wanted to have a probability map to indicate what's the likelihood of each location was a cryptic refugee. So this was our goal. And the Bayesian hierarchical model is a very powerful tool for this type of purpose. But the Bayesian hierarchical model only provides a framework. So we needed to really build what kind of models in this framework. And the models should depend on the characteristics of data and your problem. So for our data, the SDM data, the model data, the species distribution model, the scientists think this model data actually is better to be used as screener. So it can tell you whether this area would have would be a refugee or not be a refugee. So it won't do a great job to tell you what's the probability of this region, this location be a refugee. So because of that, and then we transform this data into binary data is 0, 1 by thresholding the probability this data has. And then for genetic data, I said it arguably more closely represent the refugee. So in our model, we will reflect this information. So, so after we transform the SDM data into binary, so those are the data types we have. We have binary SDM data, and we have probabilities derived from pollen and the genetics. So those are post-processing. After post-processing, we got the probabilities from pollen and the genetic. So we have those three data sources, and our model will be based on those three data sources. And to introduce it, before we introduce the model, I wanted to introduce a few notations. So first is the probability. The P is a P of S is a probability of location S being a refugee. So this is unknown and is our primary interest. We want to estimate that. We will use a logistic model to model the binary SDM data. So I use a PMS to denote the probability of a site S being a refugee according to the model data. And then we also wanted to build a relationship between the probabilities of a pollen and the genetic with this unknown probability. But the probability is only between 0 and 1. So when we build the linear models, let's say, the linear model does not like the data between 0 and 1. So we wanted to do some transformation. So we use inverse integral probability transformation to transform the probability into the real line random variable. So we have a YP and a YG. Those are transformed data. And we also transform this PS into unknown mu plus mean zero Gaussian random process XS. So our goal now will be estimating mu and estimating XS. So once we have that, and then we can transform them back to get the probability of location S being a refugee. So based on that, this is our model. So this is the logistic model for SDM data, and this is the relationship between the pollen data to the unknown probability and the genetic data to the unknown probability. So because genetic data we think is more close to the real data, we directly put this genetic data as the the true probability plus errors. But the pollen data, we still allow it to have additive bias and multiplicative bias. To put a model for genetic like that also helps us to solve the identifiability issue. Otherwise, the model will not be identifiable. And the caveat for this model is here. So for this error process in this logistic model, we put the variance to be spatially varying. It's not a constant variance. And the reason is because for the SDM data, the model data, it's more certain if this region is not a refugee, because it's mainly if they are very certain, if they think this region is not a refugee, it's mainly because this region is totally covered by ice sheet, so there is no possibility that any species can survive. But if the SDM data said there is a refugee here, and then the probability or whether it is really a refugee, this has higher, more uncertainty. So because of that, we make the variance to be spatially varying. So when it's in the region that it is a refugee, it has more variance, but otherwise it has less variance. And then after we built this model, we did some numerical experiment to study, to evaluate whether our model can really estimate the true probability. So this shows two examples of our numerical experiments. And in those examples, for this column, we have the experiment that we have 1,000 locations with model data, and then 15 locations have pollen data, and the 60 locations have genetic data. So this is more close to the true setup of our real data. And then after we apply our model, and this is the true probability, the target probability, and this is our estimate. So you can see that in this setup, we can capture some of the features of the true data, but it's very blurry, so it's not the ideal situation. But this is kind of like what the true data gave us. So we further try to study whether the blurry is really because we don't have enough data, or is because our model is inadequate to estimate the true probability. So we did a second experiment. In this experiment, we get dense data for all those three categories. So we have 1,000 model data, pollen data, and genetic data. And with those dense data, and this is our estimate. And now you can see the estimate is really, really close to the true target. So that means our data is fine, and our estimation method is fine, but the sparsity of the data limit the capacity of our estimation, the performance of our estimation. Excuse me, but this is something that I think is beyond what statistics can do. So applying those methods, and we get the refugee estimate of green alder and white spruce, and we also provide the uncertainty estimate of our probability estimate. So this provides a map of how likely each location is a refugee. So we have three. So this project, I worked with my current student, Mo Campos, and three scientists from plant biology. And they like this. They are very happy with the result. They think actually by combining three data sources, we show something that previous studies have not shown. So compared to them, I have a very limited knowledge about paleoecology, but I think if they're happy, we're happy with that. So this is the summary of the first example I showed. We proposed a Bayesian hierarchical model to combine genetic, pollen, and model data to try to uncover cryptic refugee in many years ago. And our model reflects the characteristics of different data and how their relationship to the true probability. So our study helped to find the answer for the well-known quaternary conundrum, whether there is cryptic refugee or there is species extinction. And we found that the capacity of the Bayesian hierarchical model can be limited by the scarcity of pollen and genetic data. And this may give guidance for field workers to collect, find the regions to collect more data in Eastern Beringia. So this is the first example I want to talk about. If you have any question, please feel free to stop me anytime. So yes, any question for the first example? And then if no question, I'm going to talk about a second example, the crop yield prediction using Bayesian spatially varying functional model. This is a joint work with Yunju Park, who is assistant professor at UT San Antonio. She graduated from our department a few years ago. And I want to also mention Yehua Li is currently, he's at UC's Riverside, but he's also a Texas A&M alumni, roughly the same time as me, graduated the same time as me. So agriculture, it provides food to us. So we know agriculture is very important in that regard, but it also plays a very important role in the US economy and in the global economy. So in 2019, it provides 11% of the total US employment. That was before pandemic. Pandemic changed the structure of many things. So maybe after pandemic, it will change to some other percentage. In the Midwest is one of the world's largest crop production areas. After I left Texas A&M, I spent 2 years in Colorado, and then I have spent 14 years in Midwest. So I have seen how much corn and soybean field in Midwest region. So the Midwest produced 85% of US corn and soybean. Timely and accurate yield prediction is is crucial for policymakers to manage the agricultural risk, the food crisis, and also to come up with appropriate strategies for storage, distribution, and the trade of products. So how should we make a prediction for crop yield? The weather, so it has shown that the weather, especially the temperature and the precipitation, has a significant impact on the plant growth and also consequentially affect the agricultural productivity. So it has shown that 60% of corn yield and 36% of soybean yield in Midwest were explained by climate variability. So because this is such an important problem, many studies have tried to make a prediction of crop yield, and some are based on simulation models based on how the plant grow, and some are statistical models and machine learning methods. And the last one here, the functional regression models. This is by Raymond Wang, and Raymond is also associate professor in statistics at Texas A&M University now. They used the functional regression models to make prediction for crop yield. So in Raymond's paper, they use meteorological variables, the maxima and minimal temperatures, and they also use annual precipitation data. And they treat the maxima and the minimal temperatures as functional data in their predictive model. So I think that makes a whole lot of sense, because the temperature data, how the temperature data affect the plant growth is not like an average annual temperature affect the growth. It's like a daily variation, the curve, the total curve affect the plant growth. So to use this whole trajectory as the functional data in the predictive model, I think it definitely will improve the result. So we also wanted to treat the temperature data as functional data. And for functional regression methods, there are many types of functional regression models proposed, like functional linear models, functional additive models, and a functional linear partially linear function additive model in Raymond's paper, and also functional additive mixed model. So I don't want to spend the time on the detail of each of those models, but they are very useful. However, for the data observed over large spatial domain, let's say if our data observed over several states, and for such data, there are some other important things that those models are not able to deal with. So one is the spatial dependence between functional covariates. So if your functional data, temperature data observed over spatial domain, and then there likely will be spatial dependence between those functional data. And more importantly, if your data observed over large spatial domain, and when you look at the Y and the relationship between Y and your functional covariate, it's hard to believe that the relationship would be homogeneous or should be the same across the whole spatial domain. And if it's not the same, if it's a heterogeneous, and if we ignore this heterogeneous association, and then we will have some local bias when we use a homogeneous model. So those are the things that I think important for functional data observed over spatial domain. And because of that, we propose a Bayesian spatially varying functional model for crop yield prediction. And in our method, we take into account spatial correlation in the functional covariate. And we also take into account measurement errors in functional PCA estimation. As a research student, I think it's our duty not to ignore measurement errors. But of course, I think for the temperature data, especially the local temperature data, it's very well known that it has lots of noise. So I think it's more appropriate to consider measurement errors. And in our model, we allow spatially varying relationship between crop yield and meteorological variables. So we allow that each county, each region can have their own relationship. And we also further allow the heterogeneous association, we incorporate Bayesian variable selection. So at each location, it can select different variables in their regression model. So we try to make it flexible to capture all the features in the data. So now I wanted to introduce our data. So we have crop data. This is the average corn yield data at a county level over 5 states. The 3 very famous I states, Illinois, Indiana, Iowa. Those are the 3 famous I states for corn yield prediction. And Kansas and Missouri, those are also on the Corn Belt, the very well-known Corn Belt in the United States. And the data is annual average from 1999 to 2020. So those are 21 years data. So there are 542 counties in those 5 states, but because some counties have very little data, and we almost think those probably the urban areas that may not have much land. So we discard those counties, and we only analyze the data on 403 counties. And we also have meteorology data, the county level daily max and minimal temperature data, daily and minimal temperature data. And we treat them as bivariate functional predictors. And we also have annual precipitation. This is the scalar covariate. So the reason that why we treat temperature data as functional and precipitation data as annual as a scalar is because the previous literature has shown that the cumulative precipitation seems like a better predictor. So do not need to use the the time series of precipitation data in our predictive model. And so when I talk about the heterogeneous relationship, this is our conjecture, and I think it's a very reasonable conjecture. But we still need to look at the data and see if the data suggests those features. So for our data, we first, so our data is a county level data. So we first fit a linear regression model at each county. At each of the county, we use Y as crop yield, and then we treat the temperature data, the bivariate temperature data as bivariate functional data, binary functional predictor, and we use FPCA, and then we choose the first PC and the second PC as a covariate in the linear regression model. And so this is the coefficient for the first PC. This is the coefficient for the second PC. So you can see that the coefficient actually varies quite a lot across counties. It could, even the sign could be different. And also, it seems like spatial clustered when they are close by and the color seems closer. So that means there are some spatial correlation. And we did do Moran's test to evaluate the spatial correlation, and we found the p-value is very small for that. So those preliminary results suggest that we indeed do need to account for the heterogeneous relationship, and also there are some spatial correlation around there is spatial correlation for the coefficients of the PCs. So now I wanted to introduce our model or method. So first, some notations. We use Y to denote the average corn yield at location at county S, and then X are the functional predictors. For us is the bivariate predictors, or the maximum and minimal temperature trajectories, and the Z is the annual precipitation is a scalar predictor. And we propose a spatially varying functional model. So Y is the corn yield, and this is spatially varying intercept, and this is the precipitation, scalar precipitation, and the alpha is the spatially varying coefficient, and X is a functional covariate, and the eta is a spatially varying functional coefficient. And this is a residue. So for this is the basic model for our prediction, but there are still a few things we need to take care of. One is for the functional covariate. Functional data is infinite dimension, so we cannot use infinite dimension to do the empirically. In practice, we cannot use that. So we have to figure out how to reduce the functional data into low dimension representation, and then we also wanted to estimate the basis function of the functional covariate. So in some studies, it's often just use the functional PCA and then use those as a fixed basis function. But we think that would kind of ignore the errors, the uncertainty related to the PCA estimation. So we wanted to estimate the basis function. And we also need to consider the additive measurement errors and the spatial correlation in our functional data. Finally, in our data, because we can have many PCs, functional PCs, so we needed to do a variable selection, which PCs to be included in our model. So we wanted to make it as flexible as possible. So at each county, it has its own variable selections scheme. So it can select different PCs at different counties. So for all the coefficients, let's say this coefficient, the alpha, and this coefficient, the eta, the functional coefficients, and also the intercept, because the data showed spatial dependence. So we wanted to regularize those coefficients to make them correlated process, so they would not have the degree to vary independently at each location. So after considering all those things, so I will skip all the technical details. And this is the model we come up with. So now we have intercept, and we have this scalar. And now you can see it's not the integral already removed. So we reduce it to a finite dimension. And so here is to consider the measurement errors. This is the functional covariate plus additive measurement errors. And those priors, the process level, the priors give all the spatial correlated process to the alpha, the coefficient alpha and the coefficients beta. So basically, though these models takes care of everything that I mentioned in the previous page. And then almost every method we want to do numerical experiment to give us confidence our method is working fine, and what's the performance of our model compared to the existing methods. So we compared to partial linear functional additive models, and also functional generalized additive model and functional linear models. So I just wanted to show very simple results of our simulation. So those three plots represent scenarios with strong spatial correlation in the data and a moderate spatial correlation and a weak correlation. Oh, I'm sorry. This is a weak correlation, this is moderate, and this is strong correlation in the data. So those are the mean square. So mean prediction square error, mean square prediction error of the crop yield prediction. So you can see for all those three scenarios, our model achieves the lowest mean square prediction error. So that means by allowing the model to have a varying relationship and considering and using and by considering measurement errors, we can achieve better results, better prediction. And this is a example of residues over the Iowa state. So in our simulation, we always try to simulate data as similar to the real data as possible. So we directly generate the data over the 5 states. So we take one state, Iowa, to look at the residues. So you can see that this is from our model, and this is from the competing models. So the residues from competing models are more spatially clustered. Because they didn't capture all the local variability, but our the errors from our model is much less spatially clustered. So that means we captured more variability in the data. And then we apply our method to the real data, the crop yield prediction. We still try to evaluate our method and compare to the competing method. And now also we added two, under the request of a referee, we added two more modern methods, the neural network, the deep learning methods, and the XG boost. So we use two types of MSPE. One is the regular one, and the other one is weighted mean square prediction error. The weight is by how much land, how much cropland in this county. So if it has more cropland, we give it more weight. We think that makes more sense. And so this is a result. So you can see that our method still achieved the smallest mean square prediction error compared to all these other methods. The XG boost, this one is very competitive. It's a Kaggle winner. It is very accurate, and it's quite close to our method. But still, I think ours is better for this data. And we found the neural network is very sensitive to the tuning parameters. We have to spend quite some time to tune the parameters, we are not sure whether we tuned the best, but that's the best we can do for this data set. And this shows an example that how our estimate compared to the true values. So the black dots are the true values, the triangles are our estimate, and the bars are the credible 95% credible intervals. The length of the credible interval varies. This is because the cropland size is different. So the variability for because the corn yield is average corn yield over those cropland. So when it's large, and then the data has low variability. So this is the variability of the length of a credible interval. And this is to show the coefficients in our model, estimated coefficients in our model. This is the intercept, and this is the beta 1, beta 2, and beta 3 for the functional covariates. So again, we can see that the coefficients are spatially varying, and those yellow dots indicate whether the PCs corresponding to this beta is selected into the model using our variable selection scheme for each county. So yeah, for all those three coefficients, we can see that they are spatially varying, and they are clustered also. Definitely some regions have higher, some regions have low, and even the sign can be opposite. And to further look at the breakdown of the contribution of each type of a covariate, we make this plot. And it's a little complicated. So first, for this column is Illinois, and for this column is Iowa. Iowa, I think. So let's just look at for Illinois here. And for the upper one, this is use the Bayesian. This is our method using the spatially varying coefficient model, and this is use the invariant model. So basically, the models are the same across all counties. And then the yellow part represent the variability captured by precipitation, and then the purple one is the variability captured by both precipitation and also the functional covariate, the temperatures. So you can see that precipitation actually captures relatively smaller variability of the data compared to the functional covariate. And the most interesting is compare this one and this one. This is by allowing spatially varying association, and this one does not allow spatially varying. So you can see how much variability the purple one can capture compared to this one. So yeah, I see someone, I see Elizabeth raise a hand. Yes, please.
Yeah, hi. This is all very interesting, but I'm wondering about the use of annual rainfall as a predictor rather than using the timing of the rainfall, because especially this year in this area, which is Massachusetts, there's been a drought, but it's the timing of the rainfall that really seems to make a difference in crop yields frequently. And I wondered if you considered incorporating the timing of the rainfall in your models.
Yeah, that's a great question. When we did this project, we kind of followed the previous literatures and used the precipitation as a scalar. But I also wonder whether this is the case. And then later, just a couple months ago, when I was at Sandia, I met someone whose husband is a farmer, and she said she thinks the precipitation, actually the daily variation matters too, and it could be also very important factor. So currently we are continue looking at, we're working on a follow-up project on this. And in a follow-up project, we will treat precipitation data also as functional covariate. So yes, so I think that's a very great and a valid concern for this.
Thank you.
Yeah, thank you for this question. Any other questions? Okay, if no other question, I will just move on. And then So I talked about the variable selection at each county. So here I just wanted to show that this is the real variable selection. And we show that the probability, the posterior inclusion probability of the first and the second PC scores to be included in our model. We use Iowa. We keep using Iowa as example is because Iowa has a smaller number of those gray counties that the county do not have data. So Iowa probably has more croplands than any other states we considered. So that's why we use Iowa for illustration. So the counties with the higher probability, those are the counties that will select this PC into the model, but with the low probability, then the first PC will not be included. So this is the summary for our second project. We developed a Bayesian spatially varying functional model for crop yield, basically the corn yield prediction over 5 Midwest states. We treat the maximum daily temperature as spatially dependent functional predictors and with measurement errors. But in this project, we treat the precipitation as a scalar. But as I mentioned, and Elizabeth raised this excellent question, we will consider precipitation also as functional covariate in our follow-up project. We allow for idiosyncratic response predictor relationship. And we also allow for spatially heterogeneous variable selection. And the model we found that our model outperforms other spatially invariant functional regression models. But we also are aware that some, not just weather affect the plant growth, the soil properties and irrigation, like those type of things also affect. So if we have such data, those data are more difficult to get, but if we have such data, I think they would be able to improve the results. So I think I am gonna stop here. The third one that was with my current student and with Trevor Harris, but I don't think I would have time to get to this, but I'm happy that I finished the first two. Thank you very much for your attention.
Thank you very much, Bo. Very nice talk. I guess the spatial statistical modeling and environmental statistics, they are hot topics now, especially these days. So it is really good that we had some graduate students listening your presentation. I'm opening the podium for the questions to Bo. Any questions or comments?
Should I stop sharing? Maybe I should stop sharing. So. Oh, Ritam. Hey.
Hey, Bo.
Hey.
For your second project, what sort of meteorological data are you using at, like what sort of resolution? And do you think that affects the quality of the spatial effect to the actual crop?
So we used the county level meteorological data from now on. So I think they aggregated the data to each within each county, because our crop yield data is the county level, so we don't have like location specific crop yield or land specific crop yield. So yeah, in that case, and then even we have higher resolution meteorological data. I'm not sure. Yeah, I don't know the answer. I'm not sure whether it will help or it will not help, but this is a great question. Yeah.
As a quick follow-up, and maybe that's partially the answer to your question, the phrase that you had about the idiosyncratic relationship, does it basically mean that because it's functional data, like differences of how different crops require different weather conditions, that is being represented through that idiosyncratic relationship?
Oh, that idiosyncratic relationship was for each county, the relationship between crop yield and the precipitation and the meteorology, the crop and the meteorology data. So because each county could have different, the land in each county may have different soil properties, the relationship between the crop yield and the meteorology data probably is different. And we allow them to have different relationships. So that's what I was talking about.
That makes sense. Thanks.
Thank you. Yeah.
Any more questions for Bo?
Oh, my friend Jixun, my fellow student.
Yeah, just if anybody have any question, then let you guys ask. I just show up, say hello to my classmates. We were classmates in, I think it's 2004. I graduated from department, and since that I always work in finance industry. Not do any research anymore. Today, yeah, we are so proud of Bo's achievement as a classmates. So you did a very good, fantastic presentation, and this presentation brought me back to classroom. And the difference is, you are the professor, I'm the student.
No,
Yeah.
you are the banker. Yeah, I'm very glad to hear all your achievements in the past you made. Yeah, I'm very happy to see you here, and thank you for your very nice, very kind comments.
Thank you.
Yeah, thank you.
Hi, yeah, everybody.
Any more questions? I saw the hand with Robin Way.
Oh, sorry, that's not a question. It's just a collapse.
The best
Playing with
question.
Zoom. Okay.
Yeah, best question. That's...
Any more questions? We have time for one short question. It is 11:58.
What models do Michael? I see Michael asking, what models do commodity trade use? Oh, that's a very hard question. I'm sorry, I don't think I know that. Whether the commodity trade business use. Sorry. Do you know, actually, do you know anything related to commodity trade? I would be interested in learning. Where's Michael? Don't see Michael. Oh, Michael is there. So Michael, do you know anything related to commodity?
I would just suggest that they have to rely on some kind of probabilistic models and predictive models to do their commodity futures pricing. And
Yes.
And so I would just be curious to know, how your modeling approaches compared to an industry that, basically is pricing its futures on outputs. It would be an interesting comparison.
Yes, right.
I don't happen to know what those models are. I just wanted to know, since they're related, you're basically trying to predict the same the same dependent variable, which is future crop yields.
Yeah, so I'm also interested in what models they use. I haven't really got any connection to commodity trade business, so I don't know what they use. But I'm very interested in learning that. Maybe I'll do some research and see if
Well,
it's online.
You might also be able to monetize your research if you find that you have developed a more successful modeling technique for crop yields. You might make a fortune in commodity trading.
That would be great. Thank you. Yeah, I can donate back to, if I make lots of money, I can donate back to the department.
Well, it is 12 o'clock sharp. Well, thank you very much for nice talk. And we are concluding our session.
Thanks, everybody. And thanks, Brandy.